carbon needs to return to the air to warm the planet back up, where does it come from?
Well, the rocks at the bottom of the ocean, right. But how do they get back into the sky if they're buried underwater?
Plate tectonic.
Ugh, the moving continents.
Earth's crust isn't a solid, unbroken shell. It's broken into these massive moving plates. Over millions of years, the ocean floor slowly slides beneath the continental plates, a process called subduction.
Okay, so the rocks get pushed down.
Those carbonate rocks are dragged deep into the Earth's mantle, where the intense heat eventually melts them down,
Releasing the carbon.
releasing the carbon, which then finds its way back up to the surface and erupts out of volcanoes as carbon dioxide gas.
Wow, so if the planet is totally frozen and the rain has stopped, the volcanoes just keep steadily pumping CO2 into the atmosphere. The gas builds up, creating a thicker and thicker greenhouse blanket, trapping heat until the ice finally melts and the rain starts again.
It is a majestic, slow-breathing mechanism. The carbonate-silicate cycle takes millions of years to balance itself, but it has been the absolute guardian of our planet. It is the primary reason our oceans have remained liquid for billions of years.
It really is a symphony of moving parts. You need the right star at the right distance, you need a planet large enough to keep its core molten so you have a magnetic shield, and you need liquid oceans and active plate tectonics to run the thermostat.
And if just one of those geological instruments goes permanently out of tune, the whole symphony collapses into static, the planet dies.
That is a staggering amount of conditions to meet. But here is where the puzzle gets truly wild. Because even if you have the perfect planetary spaceship orbiting the perfect stable star, you are still completely doomed if you park that entire solar system in a bad neighborhood.
Right. We have to zoom out again. Far out. We must leave the solar system entirely and examine the grand architecture of our home galaxy, the Milky Way.
This brings us to layer 3, the galactic habitable zone, the real estate market on a macro scale.
For a very long time, astronomers just assumed that a star was a star. If you found a G-type yellow dwarf on the outer fringes of the galaxy, or one buried deep in the center, they assumed it had an absolutely equal chance of hosting a habitable planet.
I mean, it seems logical. Laws of physics are the same everywhere, right?
The physics are the same, sure, but the building materials and the local hazards are vastly different. The concept of the galactic habitable zone was pioneered in the late 90s and early 2000s by scientists like Guillermo Gonzalez, Donald Brownlee, and Peter Ward.
What do they find out?
They realized that entire vast swaths of a galaxy are fundamentally hostile to life because of two competing forces, metallicity and radiation.
Okay, let's start with metallicity and look at the outer edges of the Milky Way, the galactic rim.
To understand the outer rim, we need to translate how astronomers use the word metal. To a layperson, a metal is, a sheet of aluminum or a steel beam.
Remember, shiny stuff.
But to an astrophysicist, a metal is literally any element on the periodic table that is heavier than hydrogen and helium.
Wait, so oxygen is a metal, carbon is a metal.
In astronomical terms, yes. After the Big Bang, the universe was essentially just a massive expanding cloud of hydrogen and helium gas. Every single heavier element, the carbon in your DNA, the oxygen you breathe, the silicon and iron in the Earth's crust, was forged much later.
Forged in stars.
Exactly. They were created inside the crushing nuclear cores of ancient stars, and then violently dispersed out into space when those stars exploded in supernovae.
So to build a rocky planet like Earth, you physically need the debris of dead stars. You need those heavy metals.
And this is the massive problem with the outer rim of the galaxy. It is a cosmic desert. Out on the fringes, the star density is very, very low. There simply haven't been enough generations of stars living, dying, and exploding to seed those regions with heavy elements.
So the gas clouds out there are still mostly pristine hydrogen and helium, just like the early universe.
Exactly. A star can form out there, and it might even pull together enough leftover gas to form massive gas giant planets like Jupiter or Saturn. But you physically lack the raw construction materials to build an iron core, a rocky crust, or carbon-based biology.
You literally can't build a brick house if you only have air and water. The outer edge is just barren of the necessary ingredients.
So if the outer edge is totally barren, logic might suggest we look in the exact opposite direction.
Right, we could head straight for the galactic center. Downtown Milky Way, there are billions of stars packed tightly together down there. Millions of supernovae must have gone off over the eons. It should be absolutely choked with heavy elements and metals to build planets.
It is incredibly metal-rich. You could construct rocky planets by the billions near the galactic center.
But I'm sensing a massive trap here.
The galactic center is a hyper-lethal cosmic war zone.
How bad is it?
Well, the first major issue is gravitational chaos. The stars down there are packed so densely that they frequently pass very close to one another.
And when a massive star passes close to another solar system,
Its gravity wreaks absolute havoc. It can easily grab a planet, rip it completely out of its stable habitable zone orbit, and fling it into its own sun, or just hurl it out into the frozen void of interstellar space as a rogue planet.
so your neat little 1.0 AU orbit gets totally scrambled.
You cannot maintain the billions of years of orbital stability that life requires if your planetary system is constantly being jostled by noisy, massive neighbors.
And that's just the gravity. What else is down there?
The far more terrifying issue is the radiation. At the very heart of our galaxy sits Sagittarius A, a supermassive black hole, and it is surrounded by dense clusters of massive O and B type stars.
The roaring bonfires we talked about earlier.
Yes, the ones that live short lives and explode violently. Because stellar density is so high, supernovae are going off relatively frequently in the galactic center.
And what happens if you're near one?
If a habitable planet is anywhere near a supernova detonation, the sheer blast of high-energy X-rays and gamma rays is devastating.
Does it physically blow the planet apart like the Death Star?
It doesn't need to. The ionizing radiation tears straight through the atmosphere, literally splitting apart nitrogen and oxygen molecules. These recombine into nitrogen oxides, which rapidly and completely obliterate the planet's ozone layer.
Oh, the shield that blocks ultraviolet light from the sun.
Exactly. Without the ozone layer, the planet's surface is completely sterilized by ultraviolet radiation from its own sun. And in the dense galactic core, you are also at much higher risk for gamma ray bursts, which are the most energetic explosions in the universe.
So it's a shooting gallery.
The environment is simply too explosive and too radioactive for complex life to survive the billions of years of trial and error evolution requires.
So the outer edge of the galaxy is a desert with no building materials. The center of the galaxy has the materials, but it is a literal shooting gallery of exploding stars and rogue gravity that will sterilize any biology trying to take hold.
Which leaves us looking for the middle ground, the galactic habitable zone.
Another Goldilocks ring, but this time on a sweeping galactic scale.
Researchers model this zone as a large ring sitting roughly between 20,000 and 29,000 light-years from the galactic center.
And where is our solar system parked?
The sun is located approximately 26,000 light-years from the center.
We are right in the middle of the sweet spot, again.
We are safely nestled in the quiet, boring suburbs of the Milky Way. We are far enough inward to have inherited enough heavy elements from ancient supernovae to build the Earth and our carbon-based bodies. But we are far enough outward to be completely safe from the lethal radiation and gravitational chaos of the dense downtown core.
When you stack all of this up, it genuinely feels like an impossible lottery. We won the galactic location lottery. We won the stellar type lottery with our stable yellow dwarf. We won the orbital distance lottery. We won the planetary size lottery to keep our magnetic core churning. And we won the geological lottery to have a functioning carbonate silicate thermostat.
It is the ultimate alignment of cosmic variables. It actually forms the basis of what astronomers call the rare Earth hypothesis.
What's that?
It's the idea that while simple microbial life might actually be common in the universe, the precise multi-layered gauntlet required to harbor complex, intelligent life makes planets like Earth exceedingly, vanishingly rare.
It makes you feel incredibly fragile. If this incredibly specific fragile mold is what it takes, we might be the only ones here. Which I guess brings us to how we're actually looking for these needles in the haystack. How do we even find them?
Well, the technology has exploded in the last 30 years. We don't just guess anymore. We actually search for exoplanets.
Exoplanets being planets outside our solar system.
Right. And we use a few incredibly clever methods. The most famous one right now is the transit method.
How does that work?
Imagine looking at a bright car headlight miles and miles away down a dark road. Now imagine a tiny moth flies right in front of that headlight.
The light would dim for a split second.
Exactly. When a planet orbits in front of its host star from our perspective, it blocks a tiny fraction of the star's light. The Kepler Space Telescope and now the TESS mission stare at millions of stars just waiting for that tiny periodic dip in brightness.
Wait, really? A planet is so small compared to a star The dip has to be microscopic.
Is a fraction of a percent. But our sensors are that good. There's another method, too. Radial velocity.
Radial velocity.
Yeah, we talked about how the star pulls on the planet with gravity. Well, gravity works both ways. The planet is actually pulling slightly on the star, too.
Oh, like two people holding hands and spinning? The big person still wobbles a little bit.
That is the exact physics. As the planet orbits, it tugs the star slightly toward us and then slightly away from us. We can measure that tiny wobble by looking at the star's light spectrum shifting. It gets slightly bluer as it moves toward us and redder as it moves away.
So we can find them. We can locate the planets in the habitable zones, but how do we know if they actually have life? We can't travel there.
No, but we can look at their air. This is where the James Webb Space Telescope, the JWST, is completely revolutionizing the field with atmospheric spectroscopy.
Atmospheric spectroscopy. Okay, break that down.
When that tiny moth, the planet, passes in front of the headlight, the starlight doesn't just get blocked. A tiny fraction of that starlight actually filters through the planet's atmosphere before reaching our telescopes.
Ah, and the gases in the atmosphere absorb certain colors of that light.
Precisely. Different chemicals absorb different wavelengths of light. By looking at the light that reaches us, we can essentially read a barcode of what chemicals are floating in that alien sky.
What chemicals are we looking for?
We are looking for biosignatures. Gases like oxygen, ozone, methane, and carbon dioxide. Specifically, we are looking for combinations that shouldn't exist together naturally.
Like what?
Like oxygen and methane. Methane breaks down very quickly in the presence of oxygen. If you see a lot of both in a planet's atmosphere, something must be constantly pumping them out to replenish them. On Earth, that something is life. Cows, bacteria, plants.
So if we see that barcode, it's a massive flashing sign that something is alive down there.
Exactly. It's our best shot at finding a second Earth.
But this all circles back to the Drake equation and the Fermi paradox, right?
Oh, absolutely. The Drake equation is basically a mathematical argument to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way. It factors in star formation, the fraction of stars with planets, the fraction that might support life.
And the Fermi paradox is the ultimate follow-up question. If the